Okay, today we will study about how to solve the carbonic equations which governs the beam deflections. In last week, we derived the beam carbonic equation is simply EI, which is the bending stiffness, and V is the deflections, and 4 times of derivative equal Qx. Q is the distributed load, which is a function of X. Actually, we had equilibrium equations. Say this is the some small portion of the beam subject to a external load Q. Q is the function of X, and please notice that X is the and this is the obert. Okay, so this is the X and that is the Y, and Q is the function of X, and we have 2 equilibrium. One is the vertical y-axis vertical equation, and we got these equations, and there is another one equilibrium equation, and this is second equilibrium equation. So, and then we combine them, we eliminate this shear force V, put it here, then we get moment, second derivative of moment is simply Qx, which is the equilibrium. Now another important equation is the moment curvature relation, and we obtain the curvature. This is the actually the curvature. We have a relation moment equal EI curvature, and this curvature is given as a second derivative of deflection curve V. V is the say we have a beam, and this is the X, and this is the Vx. Actually, we don't consider thickness, we just consider beam as just one line. Okay, this was the original beam positions, and then subject to a distributed load Q, then we have a deflections like this. That is the deflection and function of X. So this is the Vx, and we second derivative of Vx is the given as the curvature. So moment equal EI second derivative of the deflection, that is a moment curvature relations, and then this moment we substitute into here, then we have now EI, and there is a second derivative, there is another second derivative, so we finally have the EI 4 times derivative of V is given as distributed load Qx. Okay, this is a very well-known carbonic equations which describe the beam deflections under the external load Q. Q is of course the load, distributed load per unit length. Okay, this is the again the summary of the of how we derived this beam carbonic equation. Now let's try to solve this mathematical first order differential equation. So I will just say first order differential equation. Actually, let's forget all other theory, just focus on the mathematics differential equations. Okay, so simply let's say let's start with let's start with a EI. Let's forget all the even constant. Let's just given as the Vx and 4 times derivative equal Qx. Again, as I said, let's forget all the beam theory. We just focus on first order differential equations, and it is given simply as a function of x. Of course, Qx is a given, and Vx is the one we want to solve. And for the beam case, actually, we have a 2 boundary condition on the left and the another boundary condition on the right. Well, what does it mean? Well, here is the 4 times the derivative, and I will draw the beam like that. Beam like that, and there will be a boundary condition. There will be boundary condition on the left hand side and another boundary condition on the right hand side. I will say here is the x equals 0, and here is the x equal L. And here we have a 2 boundary condition. Okay, 2 boundary conditions. And here another 2 boundary conditions. So totally 4 boundary conditions, and Q is given. Now how to solve the Vx, 4 times of derivative. That's simply a mathematical, very simple differential equation, first order differential equation. I'm sure you already know about this differential equation, but let's try to remind ourselves of these procedures. Okay, let's say we have this kind of problem and try to solve. Okay, what will be the first step? Well, simply, since there is only 1 term of the first derivative, we simply integrate 1 time. So this 4 times will be just 3 times. Integrate, just integrate on the both sides, and Qx will be dx, and then there will be simply a constant, integration constant, C1. Okay, that will be a constant. And then we integrate 1 more time. So integrate 1 more time. So third derivative will be simply second derivative, and there we can integrate 1 more time. Please keep in mind that Q is already known, so it's no problem to integrate 1 time and second time and so on and so on. And now here we need to integrate, so C1 times x, and now there will be another integration constant, let's call C2. Okay, let's integrate 1 more time, and so V prime, and this will be now another time Qx, and integrate 1 more time, and then this constant we need to integrate, so C1 over 2 and x squared plus C2x, and then C3. Just one last step, integrate 1 more time. We finally get a Vx, and we integrate 4 times of Qx, and then dx, 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 and plus now 6 times C1 and x3 plus C2 and 2 and x squared plus C3x and C3x and plus C4. Okay, So this is the solution we obtain by integrating 4 times. Now here we obviously have a 4 integration constant C1, 2, 3, 4, which will be obtained using 2 boundary conditions at given x equals 0 and another 2 boundary condition at given x equals L. So total 4 boundary conditions. These four boundary conditions will be used to calculate all these C1 and C2 and C3 and C4. So this is a simple, very clear procedure to get this all Vx, okay, deflection curve. So I want to like to emphasize that we start with a given Qx, okay, that should be a given Qx, and Bx, two boundary condition and another 2 boundary condition should be given, okay, and we just integrate. Finally, we will get the C1, 2, 3, 4 using those 4 boundary conditions. Let's try to solve, use this procedure to solve the a very simple beam case. Okay, so let's just copy and okay, let's put it like that. Okay, so let's apply these steps to a very simple case, such as the beam. Okay, this is the beam. We just neglect the thickness. We just represent the beam by line, and at both sides we have a clamped, and then there will be a simply subject to a uniform distributed load like that. So this is the certainly one case where the beam is subject to a uniform load and clamped on the left and also clamped on the right hand side. So this is very typical problem case. Well, before we solve this problem, let's try to imagine what kind of a bound deflection curve we would have. We don't know. Of course, we have to solve all the differential equation, but we can estimate deflection curves like that. Okay, so it's important to be able to predict this kind of a deflection. Where this beam will not deflect like that. Nobody should not expect a deflection curve like that. Well, why not? Well, simply because at the clamped, this has to be very much flat. And here is also the flat. That's very important in clamped. So we should not have this kind of boundary condition. Anyhow, this is the case, I will just call case 1. a uniform load. So uniform load Qx now is the Q, which is the applied distributed load, and this, let's try to express this uniform distributed load as a function of Qx. Well, this magnitude, first of all, this magnitude actually, let's denote this as the Q0, and then please notice that there is all downward. So Qx is simply minus Q0, right? Q0 is a constant, and there is the downward, that's why there's a minus. So this is the Qx and minus Q0, and now the boundary condition, here, well, deflection will be certainly 0. So our at equals 0, deflection will be 0. And then, very importantly, the slope will be 0. Now, what does it mean, slope? Well, slope is always given as the first derivative. So first derivative at 0 should be the 0. And here, similar to left-hand side, since it's clamped, V at L equals 0, deflection is 0, and the slope will be 0. So slope is again given as the derivative, and at L equals 0. So we have 4 boundary conditions. And now we follow this step. Let's say here, I don't want to rewrite, but let's just simply follow this equation. So Qx equals minus Q0. So this will be simply minus Q0. So here, minus Q0. And so if you integrate, what will happen? Well, this will be simply minus Q0x, right? Since it's integrate. And there is an integration coefficient to C1. And integrate one more time. Well, not difficult at all. We just integrate one more time. So Q0 and second and Q square, right? And then C1 plus X plus C2. And let's integrate one more time. No problem. We just integrate 6 Q0 X3 third power. And then integrate coefficient like that. And finally, we integrate one more time. So 4 times 6, so 24 Q0 and X4. Okay, so these 4 times of integration, in this case, will be minus Q0 divided by 24 times X 4 times, first power. Okay, so here is the solution. Of course, we have to obtain this C1, 2, 3, 4 using this 4 boundary condition. Okay, so let's try to solve this C1, 2, 3, 4. And as here, the Q V is at 0 equals 0. So V 0, let's put it here. V 0. Okay, let's say V 0. V 0 here. And then this will be X equals 0, will be 0, 0, 0, 0, and only C4 will be left. So C4, okay? So V0 is simply C4. But V0, what's the value? Simply 0. So we notice that C4 is given as a 0. Now another one equation is the V prime at 0 equals 0. So V prime 0. So prime at 0 means that, of course, this one will be 0 and 0 and 0 and then C4. So V prime at 0, C3. But that is also given as a 0. So this will be a 0. So as we can see that C3 and C4 are simply all 0. Now, we need to determine C1 and C2. Well, there are another condition at V at L, x equal L. So V at L, now we have to substitute L here. So V at L, now this one, please, is no longer 0. So L means that minus Q024 and L4 plus 6 C1 L3 plus 2 C2 and L2. And what is this? Well, this one is what? Simply 0. So this should be 0. We cannot directly calculate the C1 and C2 from here, but certainly we got the one equations. And last equation will be V prime equal at L equals 0. So the let's say V prime is here. So V prime at L equal here. So minus a Q0 and 6. I'm using this here. L3 plus C12 and L2 plus C2L. What's the value? Well, value is 0. So equal 0. So we determine the C3, C4 equals 0, and the other C1, C2 can be simply obtained from these two equations. Okay, C1 and C2, and C1 and C2, and there is a term, and from this we can have C1 and C2. Well, we don't need to calculate this. We can do it, obviously. One thing I want to emphasize here, actually the governing equation for the beam is EI V x1234 equal QX, but in this case we assume we just used EI equal 1. So that was the equation. This is just for the purpose of a simplicity. Okay, I just use this constant case, but in general we have to use just EI. So in case we have EI, all you need to do is just multiply EI here, and EI here, and EI here. So you don't have to divide by EI. It's simpler, and we don't have to divide EI. Just leave it there, and then we integrate. Nothing will happen. So we just keep integrating. So we can always say left-hand side there is EI. Okay, so I hope that these governing equations and how to solve, how to determine the Vx using 4 boundary conditions from this case. Other loading case and other boundary conditions, the procedure will be pretty much simple, very simple, and I mean very similar as this case. Okay. Another very important point is that please keep in mind that this term, okay, this term is what? This term is a prime is the angle theta, and also very important, mathematically there was a second derivative of Vx, but what is this value? Physically, EI vs V second derivative. What does it mean? And there is another one, EI V third power. What is this? Well, if we go back, and here we have EI second derivative of V is simply moment, okay, moment. And also there is a equation from here, Vx is the minus a moment derivative. So this one will be minus EI V to the power, third power. Okay, so very interestingly, EI second derivative is a V, and EI third derivative will be a V, shear force of V as a function of X. So this is a very important relations, and V was just a geometrical deflection, but this one is simply moment X given as a function of X. And now this one is what? Minus Vx, shear force, which exists at each cross sections. So again, this V is deflection, and theta is the geometrical rotations, and second derivative EI times will be moment. EI times V third power is the shear force. Okay, this is the physical meaning. Vx, moment X, and theta, well, which is also function of X. So I will put it here. Okay, EI theta slope, okay, function of X, and EI, well, I will write Vx. So when we solve this fourth order differential equation, the boundary condition will be given either V theta, which is a slope, or moment, or shear force at each boundary. Okay, and in this case, we don't know the moment or second derivative. Well, we don't know shear force, which is the third derivative. In this case, all we know is about the deflection and slope, two boundary, they totally four boundary, which was enough. But depending on this a different case, such as like let's consider another case. Okay, let's try to copy this one, and then let's apply to a different case. Okay, and different case is that let's say we don't consider okay. Okay. I better save it now. Looks very unstable. Okay, what I'm trying to do is that let's try to consider a little different boundary condition, such as a free boundary condition. Okay, free boundary condition. Free means that here we can have okay, let's say very simple case like that, and then we have a, oh man, we have a certain load. So on the right-hand side is free. Well, physically, what does it mean? The free on the right-hand side. Free means there is no shear force and no moment. So in mathematically, well, I better close and reopen again. Things looks very unstable. So, okay. I made a mistake. I better close the Google Drive. I better pause it, and I better pause for the thinking. Okay. And okay, what I'm trying to say is that on the left-hand side and the right-hand side, we're going to have a two boundary condition. Sometimes the clamped, in clamped, there will be deflection 0 or derivative 0. Sometimes free. Free means that moment equals 0 or shear force is equals 0. So moment equals 0, then there will be a second derivative will be 0, and shear force is 0, then there a third derivative will be 0, because the shear force will be given as the 3 times of derivative of shear force. Okay, and so the boundary condition, we certainly need to consider many different boundary conditions, and also distribute load, Q, we could have many different types of Q. So But the important point is that no matter what kinds of boundary condition we have, no matter what kinds of distributed load we have, all these procedures solving force derivative will be pretty much same. Okay, so let's say here we consider, and here we don't consider this one, but let's consider here as the case. Okay, so in this case, I will redraw a beam. Okay, this will be the beam, but very importantly, on the right-hand side is a free. So simply the deflection curve will be like that, right? So on the right-hand side, the V shear force will be 0. So forget this. Shear force will be the 0 at L equals 0, and moment at L equals 0. But as we know, the V is the simply what given as the minus EI V 1, 2, 3 times at L equals 0, and moment equals 0 means EI V second derivative L equals 0. So we can say that third power equals 0, and second derivative will be 0 at x equals 0 at the free condition. Here, so this will be a second case, and the right-hand side is the clamped. Okay, so in this case, all the procedure will be the same, and on the right-hand side, this will be the same. Only difference will be these equations. So let's delete this out. Well, I don't like this PowerPoint. Sometimes very unstable. So this one, using this one, as you can see here, here at x equal L, there will be one equation. There x equal L, there will be, we use this one, and then we can solve the C1 and C2. That's the what we can use, right? So this one. Okay, so tomorrow I will revisit this boundary condition, but I hope you understand what I'm trying to say. Any boundary condition will give us 4 equations. From these 4 equations, we can solve C1, 2, 3, 4. Okay, that is the messages I want to emphasize. And another important case will be a Okay, let's try to close one more time and then reopen. For the boundary condition, other than this constant, well, this, I mean, not boundary, the distributed load can be also a function of the x, and simply any given x will be we can integrate one time, 4 times of a derivative for any given qx, which is not difficult at all. You can just straightly integrate the 4 times for any given x. And on the right hand side, C1, 2, 3, 4 will be given like that. So which we can use this method for any q. Okay, that's the one point. Ooh. So today I wanted to remind you of the all procedures which is needed to solve these 4th order differential equations. Again, the external distributed external load Qx and 4 times of a 4 boundary condition, and which you will use to determine C1, 2, 3, 4. Okay. I wanted to say that we could have many different boundary conditions, or we could have many different types of distributed load. But the whole procedure will be very straightforward. And another important point is that once we obtain C1, 2, 3, 4, what does it mean? We completely determine Vx. Now, once we have all the Vx, from which we can say that derivative or slope will be the given also. Second derivative, which is very important, second derivative of V is also given. Why? Well, simply we know the C1 and C2 from this boundary condition. And so this equation means moment as a function of x. Yes, is very important equation, right? And then this one, well, C1 and some function, this will give us the Vx shear force, a function of x. So when we integrate this one, this V and V prime and double prime and dot prime all has the very important meaning, and so that will be a restudied. Okay, let's try to continue to our class tomorrow. But I hope you understand my emphasis is to solve how to solve the differential equations. Okay, see you tomorrow. Okay, bye.